Let's give a little bit of background about yourself and just tell us a little bit about what you're interested in and what you're working on and that kind of stuff.
Yeah, sure. Currently I'm working as software engineer at Amazon.
Oh, okay.
Amazon global team. So basically their aim is to enable customers to buy products from all around the world. So let's say if someone from China wants to buy US products, so Amazon provides those kind of services where they'll be taking care of. So for customers, it will be like the regular experience, but behind the scenes, we have like several restrictions in place. For example, some are like legal restrictions. These products are not legally exportable. Some are more kind of business restrictions, that whether it is profitable or not. So based on that, we calculate the eligibility for each product. And if something is eligible, we let customers buy it. So currently what is going on is we are trying to use machine learning to try to improve this eligibility prediction problem based on several different catalog attributes. So yeah, those are kind of the current projects. And yeah, previously I completed my master's from UC San Diego, where I was working with Professor Julian McAuley. So that's where, I worked on multiple research projects, and this is like the paper I'm going to present is like one of the works we did there.
Very interesting.
Recently there's another paper that we published in ACL that is related to spoiler detection. So can we like build some system to automatically detect spoilers in, let's say, movie reviews or book reviews?
Very good. I'm curious, how do you mark up the legal rule sets that define whether a product can be exported or imported? That's, to me, sounds like a semantics kind of rule-based thing, and to make machine learning quite challenging.
So currently it's rule-based, but coming up with the rules. So what happens is whenever Amazon has to like enable any country for selling, so lawyers usually go.
I see. Yeah, so they would. That's what I'm saying. So there is a human process. It's a human mediated process.
But our aim is to kind of fast track that process, and that's where we are trying to see if we can use machine learning. Even though like we might come up with some rule-based system, let's say knives are not exportable to China. So there would be a text-based rule saying that if knife is appearing in some product description or name, mark it as ineligible. But there could be some T-shirt with a knife's picture on it. So in that case, that product would be kind of falsely marked as ineligible. So that's where the scope is for improvement, and we are trying to see if we can build some machine learning model to do even better than what we are doing.
Okay, and that would be based on structured data and attributes, known attributes.
Yeah. So we already have like lots of data.
Right. Very interesting.
Yeah.
Very interesting. Okay, so we're coming up to the 15-minute mark. Just very interesting. So I don't work directly in those domains. I work more in computer vision-based systems, so I don't work directly in that. But there's some interesting overlap between what you're doing in terms of the paper you're presenting and computer vision. So we might have a chance to chat about that a little bit later on.
Yeah.
Okay. All right. So in the interest of recording this for everyone, would you mind just making your way through the paper, and I will, prompt you with questions or clarifications as they come up, if that's all right.
Sure. Yeah. Sure.
Okay. All right. So I'll stop my video, and yep, you got it. Perfect.
Yeah.
That's great.
So can you see the screen?
Yep. That's all good, and you can just hit play, and that's perfect. Full screen.
Yeah. Sure. So yeah, this is one of the works I did while I was in graduate school. So it's about how we can use machine learning to uh, find sizes of clothing products so that they'll fit well to the customers. Uh, so yeah. So this is kind of a brief outline for the project, for the presentation, sorry. So first I'll be going over what is the motivation behind solving this product. Why do we need to, find products that will fit well to customers? Then I'll be going over what kind of data is required to solve this problem. Then I'll be briefly defining the goal, as in what's our goal, what is our goal to solve this problem. Then I'll be covering one kind of a baseline paper from Amazon, which was like one of the first works in this domain, and which I used as a baseline in our paper. Then I'll be talking about some of the challenges we identified in that domain and the methods we propose to overcome those challenges. Then finally, I'll be talking about what all experiments we did, results, and what are some of the future directions.
Excellent.
Yeah. So yeah, like who doesn't love online shopping, right? Because it's very convenient. It offers a variety of products, and we get great deals as well. And it also benefits retailers because it provides them greater reach for customers. But whenever we go on to buy any clothing product online, we are kind of wary of whether it'll fit us or not, because there is wide sizing variations across different brands. So for example, for the case of shoes, size 9 of Puma might not be the same as size 9 of Nike. So this is where the problem kicks in. So because of this, customers could have a bad shopping experience because they might have to return the products, and this also results in monetary losses for the retailers. So that is why tackling this problem has a huge scope and practical implications. So first thing I want to talk about, why should we use machine learning to solve this problem? So my thought process in justifying the use of machine learning for solving this problem was that fitness is kind of very subjective, right? Because for same shirt, some people like their clothes to be more form-fitting, others like their clothes to be a little bit loose. So it's very subjective and differs across various customers. Uh, so there are no set of algorithmic steps we can take to determine whether certain thing is a fit or not. So that's like the first point. And then there's a lot of data available nowadays. So that really motivates us to use machine learning to let the data speak for itself and provide good recommendations. Uh, so yeah, what type of data is available? So for Amazon or any of the big e-commerce companies, they have their like internal data stores where they store everything about customer orders. And for Amazon, the study was done on shoe products, and they mentioned in the paper that whenever someone has to return anything, they'll be taking their feedback whether the fit was small or large, and if they didn't return it, they'll assume that it was a fit. But so like I was in a graduate school, so that was not possible for me to, to get access to proprietary data. So there are some retailers nowadays which allow customers to provide fit feedback while leaving reviews. So these are ModCloth and Rent the Runway are two examples of that. So that's where I collected that data myself. And having said that, we can assume that minimally, if we have data of the form of customer ID, product ID, and fit feedback available, we'll be able to tackle this problem. So this is like the minimal set of things we need for solving this
So the
problem.
third one was labels. Oh, hi there, Mahesh. The third thing you mentioned was the labels. Can you go into a little bit of detail onto, like, you've got the product ID, you've got the customer ID, and then the labels themselves. I'm just curious, what were they, just flags, or were they scalars, or?
Yeah, so from the data set we collected, so they allowed customer to provide feedback in structured format, and they had one field where they'll be asking whether the fit was fit or small or large.
Oh, okay, so they're the
So
three labels. Got it. Okay,
that's
so
that's the
those
label.
three labels, that's all you need. Okay.
Yeah. So those are kind of three labels we have. So now we have this kind of data. So what's our goal? How can we like solve this problem? So once we have this kind of data, we can define some features for each customer and product. Features for customer can capture their preferences of what kind of fitting they like. For products, it could capture, what are the fitting, I mean, sizing or styling related properties along, various dimensions. For shoes, it could be length or width. For shirts and all, it could be, more than length or width across different dimensions. So once we define such features, our first goal is to learn such features from the data. And once we have learned it, to provide recommendations for customers. So if some customer shows interest in a particular product, we'll be, based on the features that we have learned, we'll decide which of the sizes for that particular product would fit best for the customer, and we'll recommend those.
So how do you come up with the features themselves? Are these just handcrafted features that you're using?
So if we have like this kind of data, like it's we would have to define some latent features that we'll be learning from the data. But again, if we have like more data, let's say we have product attributes, or we have like customer measurements, we can define more feature. But here the goal was to, have kind of minimal set of data and then try to solve the problem, because it will not always be the case that some proprietary data is available to public. So now we can start talking about how this paper from Amazon tried to solve this problem. It was like one of the first studies, and they did it for shoe products. And I think it was good because the fitness of shoes can be judged along one or two dimensions, length or width. So it was a good point from to start with from modeling perspective. So these are just some terms which were used in the paper. So parent product is defined as a certain product, let's say Columbia jacket, and a child product would be a particular size of a parent product. So for Columbia jacket, it would be small, medium, large. So those are kind of child product. So in the paper, authors basically define one latent variable for each customer and child product, and they interpret it as true sizes. Basically, those features would capture true sizes of customer and child products. And this true size would be different for a particular child product. It would be different from the catalog size because there is, sizing variations across different brands. So essentially what we are trying to do is kind of bring everything on the same scale, which is like the true sizes for all the products. And then against that scale, we'll try to see whether it will fit to the customer or not. So I can talk a little bit about how we can learn those true sizes. So for a customer and for a product, child product, we can define two latent features. These are just one dimensional variable. And let's say in our data set, we have this kind of transaction where customer C bought child product P and they reported it as fit. So let's say we already have the true sizes, then we would ideally want this difference between the true sizes of customer and child product to be small if that transaction was a fit, right? Similarly, if there was a transaction which was reported as small, the true size of the customer would ideally be very small as compared to the true size of the product. So this difference would be large. And similarly, if we have a transaction like this, then the size of the product would be much larger than the customer. So this difference should be large. So based on like these observations, we can, define a fit score, which will kind of quantify each transaction with a score saying that how fit that particular product was for a particular customer. And here W is some non-negative weight parameter that we'll be able to learn from the data. So now we have the fit score, but our ultimate goal is to classify our transactions into one of the three classes. So so let's say this is the real number line, and it contains various values for the fit score that we have. So here we can apply ordinal regression to do the end classification. In ordinal regression, basically we'll define two threshold parameters, B1 and B2, which will divide this real number line into three segments. And we can interpret the middle segment as, so we can say that if fit score falls in this middle segment, we will classify our transaction as fit. If it falls below B1, we can say we'll classify a transaction as small. Otherwise, we'll classify a transaction as large. So
I have
it's
a quick question. B1 and B2 are in customer space or in product space? I mean, are they?
They're kind of general, I would say.
General, okay.
It's not related to anything.
So it's not specific. So B1 and B2 would not vary by customer, and they would not vary by product. They are.
Yeah, they are kind of two more latent variables that we'll be learning from our data itself. That where should we, put these thresholds in our real number line so that we are able to classify transactions with higher accuracy.
Okay.
Yeah. So yeah. So now that we have decided to use ordinal regression, we have to come up with a loss function and an optimization technique to try to learn these parameters. So we have one latent variable for customer and product, And we also have these threshold parameters B1 and B2. And we also have this parameter W. So these all we'll have to learn from the data. And for loss function, authors use hinge loss, which is of this form. And essentially, it has a nice property of maximizing the margin. So even though some transaction might be getting classified correctly, hinge loss would ensure that uh, the confidence of that classification is higher. If it is not higher, we'll incur some loss that we'll again try to minimize. So yeah, essentially, so this is a big loss function we have, but essentially what it means is that if some transaction is reported as large, and if the fit score is greater than B2, we'll incur, minimal loss here. Similarly, for the small case, if we have fit score much larger than B1, we'll incur minimal loss in this section. And similarly, if it is between B1 and B2, the fit class would have minimal loss. So based on which of the class would minimize our loss, we'll be learning the parameters, and that will ultimately, drive our classification at the end.
Yeah, very good.
And yeah, for optimization, they use like stochastic gradient descent, which is a standard iterative optimization technique. Mm-hmm. So once they learn these parameters, they basically just fed these latent features and as features in standard logistic regression and random forest classifier to finally produce the output. So for each transaction, we have two features, UC and VP. So basically these became features for our logistic regression classifier. And then ultimately, finally, the label was the fit outcome. And that produced the final prediction. And yeah, so they did offline evaluation. So it was not possible to show recommendations to customers and get their feedback as to whether the recommendation was good or not. So they basically treated the performance of predicting fitness on unseen transactions as a proxy for how well they'll be doing in the recommendation task. Yeah. Any questions?
I have a question there. Yeah. So once again, it's not clear to me. So if I'm a customer and in the past I have said that this was too big and this was too small, and I bought 5 products that fitted me perfectly, that information is highly relevant at inference time to whether or not this particular product is the right fit for me. Mm-hmm. So that B1 and B2, those latent variables, I'm just curious how my personal data, my personal profile, as opposed to the kind of the average. I understand that you're creating an average across all transactions. I'm not suggesting otherwise, but I'm just wondering how my personal data comes into play here, and is it utilized or is it more?
So your personal data would be kind of captured in these 2 variables, right?
Right.
For customers, we have 1 variable. So that is one of the.
Oh, okay. So I would have an entry for me in the model that's specific to me. Okay, great. Okay. So yeah. So it's n by m, where n is the number of products and n is the number of people. Okay.
Yeah. And we can clearly see here that one of the shortcomings of their model was that they only had like 1 latent variable for 1 customer, which might be not very flexible in capturing, different fit preferences
Right.
of the customer. So we'll see later on like how we can improve on that.
Okay. Sure. All right.
So yeah, then we identified some of the challenges which were kind of unanswered in this original paper. So first thing was that let's say for products like dresses and shirts, they relatively have more dimensions along which fit is just. So having just one latent variable to capture all those property might not be very sufficient. Then fit preferences of the customers also vary across product categories. For example, if we are buying a jacket, we like it a little bit loose, but if we are, let's say, buying a wetsuit, that will be, more form fitting. So again, this one latent variable might not be able to capture all these kind of varieties. Then one major thing that was not addressed in the paper was that most of the transactions are reported as fit, and there is about 25 to 20% of the transactions which fall in these small and large classes. So if we are not handling that in our model kind of get biased and might not perform very well for specifically these two, scarce classes where we have less data samples. So there is kind of inherent imbalance in the data. And then last thing was there was no publicly available data set. So they had used their proprietary data set. So I had to, go through the web and collect these relevant data sets. So to address, first two challenges, we first of all used multiple latent features for each customer and product so that we are able to capture this variations, which could be, which vary from customer to customer and product to product. And then for addressing the label imbalance issue, we use metric learning technique with prototyping. So I'll be going over, what this technique is exactly. And then we also contributed two novel data sets in order to solve this problem. So this is kind of an overview of the model. So first part is learning multiple latent features for products and customers. And then there's a second step where we apply metric learning technique to improve the latent space that we have so that we can handle the label imbalance issue and can do our classification with higher accuracy. So I'll be going over each of the component next. So first thing was how we can learn more comprehensive feature for each customer and product. So we decided to use a latent factor model to capture that. So essentially, now for each customer and product, we have k-dimensional latent features. And apart from that, we have few bias terms. Specifically, we have bias terms for a particular customer and for a particular parent product. So for customer, it could capture the notion that few customers are very accommodating and like giving feedback, and few are very sensitive to fit. So they can, say something is small even though it might not be the case. I mean, they could be a little bit more sensitive. And similarly, for the products, it captures the notion that some products are reported more unfit than the other, maybe because of their inherent features. So essentially, so we have modified the fit function in this form. First three terms are the bias terms. We are concatenating everything, and then we take element-wise multiplication for each of the latent features we have for a particular customer and a child product. So any questions in this this huge function?
So the weight vector, I'm just wondering what sort of dimensionality that has.
So it's like similar to the dimensionality of the following term. So if this is k dimensional, this is 3-dimensional. So the weight would be k plus 3-dimensional.
Okay. All right.
Yeah.
Very cool. Yep. Understood.
Yeah. Yeah. So here one challenge that was also not addressed in the base paper was that, let's say we have three products, three child products. Let's say this is small, medium, and large. So let's say we are predicting that this particular product would be small for a particular customer, and that that prediction is true. And if that is the case, we should also enforce that all the products whose size is smaller than this middle product, those should also be evaluated as false. I mean, those should also be evaluated as small for that particular customer. So essentially, what I'm trying to say is that there should be an inherent order in the fitness score across different sizes of a parent product. So this constraint was kind of not explicitly enforced in the base paper. And here the problem would worsen because we now have, a lot more features. So if we don't enforce an order between the fitness score of different sizes of a particular product, we might not be able to produce recommendations. Even though fit prediction performance could improve, but if our recommendation, so during the time of recommendation for each size, we'll evaluate whether whether a particular product would be fit, small, or large. And if our model says that this product is, let's say, large, and this product is fit, and this product is small, so we can see like it doesn't make sense, and our recommendations might not be, very useful. So to handle that, we essentially enforced some constraints on the latent features of the products. Essentially, so for a particular customer and a parent product, we can see that this is the only term that varies for different sizes. So if we can enforce some kind of order for this variable, we'll have similar order in the fit scores for a particular customer and a particular parent product. So this is what we did. So for a particular product, if there is a larger size available, we'll ensure that all the latent features in the larger size are element-wise greater than the current product. And similarly, for the current product, all the latent features are element-wise greater than one smaller size for that product if that is available.
Interesting. I have a quick question. If we have two competing dimensions, let's say I have sleeve length and waist size, and I have very short arms but have a huge chest, or I have very long arms and a very narrow chest. Does this system automatically penalize things that don't fit in any dimension, so I'm left with what does, or does it create a balance between those? Or
so yeah, that is like one of the open directions for this project, because currently we can't interpret what each of those latent feature would mean,
right?
Because they are latent, and we are not incorporating any information from the reviews where user might be saying that it doesn't fit well across my chest, but it fit well on my arms, and I care more about my arms, fitness in my arms, so I'm reporting it as fit. So this kind of information we can get from the review text, so which is one of the future directions as to how we can incorporate that information.
Excellent. Understood.
Try to make
so just sorry to interrupt. So we have 15 minutes left before the hour is up. If you want to go beyond the hour, I'm happy to do that, but Sam might chop off the video at an hour. So let's try and a good place in 15 minutes. Okay.
Sure. Yeah, so essentially here we have changed the definition of the fit score and applied some constraints so that we have like more structure for giving recommendations. And then again, for optimization, we use one variant of gradient descent, which is projected gradient descent, which enforces these constraints after every update. Now, we have learned good features for each customer and product. So how can we handle the label imbalance? So that I can explain using this diagram to be quick. So let's say the features that we have learned, when we plot those features in 2 dimensions, this is what our feature space would look like. We'll have many transactions of class fit, which is kind of circle here. For small and large, we'll have relatively less transaction, and the points for fit class would be kind of spread all across the latent space because they are more and there's kind of more noise in there. So first step was to apply the prototyping. Prototyping is essentially identifying some key data points in a particular class, so that ultimately what we are left with is kind of only few data samples which provide good representation for each of the class. So essentially we are kind of sampling some key data points from each class so that we have less noise in our latent space. And now the distribution of data is balanced across each of the 3 classes that we have. And for this step, we use some kind of heuristic, which seem to work well. The more details can be seen in the paper and in the slides later on. But once we have sampled such keys, data points from each of the class, we apply this large margin nearest neighbor technique. Essentially, what it does is it will bring points from the same class closer together and will enforce a certain margin between points of different class. So essentially we will have good separation between the data points in each class, between each class. So if you compare this latent space to metric space, we can see that if we do classification using these features, or if we do classification using these features, this will definitely perform very well. So yeah, so this was kind of two methods we applied to handle the label imbalance issue and try to, clean the feature space we have so that we can produce good predictions.
Very interesting. Yep. Okay.
Yeah, so these are some of the details. Yeah, the slides will be uploaded so we can refer it. Then I'll take the remaining time to talk about the experiments. So there were quite a few variations. So first method is the method which was proposed by the baseline paper. And then the second method, instead of having one latent variable, we increase the latent variables for each customer and product to k, to try to see if we can just naively increase the parameters, would it perform well or not. Then in the third method, instead of naively increasing the parameters, we utilize the latent factor variation that we proposed in our paper, and then finally used logistic regression to produce the output. Then in the fourth variation, so it's a variation of second, and instead of using logistic regression, we use metric learning technique to produce the final predictions. And then finally, last method is the method which is proposed by us. So we have these different combinations of things which are there to basically try to, showcase the effectiveness of capturing fit semantics over true sizes, then importance of learning good representations, and then effectiveness of the proposed metric learning approach. So yeah, these were the results, and the performance was measured on the basis of average AUC score. So we perform classification on each class, calculate the AUC independently for each class, and then average it. So that gives us a good sense of how a model is performing. And this is independent of label imbalance, because AUC has that property that it doesn't vary based on whether data had label imbalance or not. So yeah, as we can see, if we compare our method with the baseline method, it's performing very well. So essentially, it could be attributed to the fact that we are learning good representations, and we are also explicitly handling the label imbalance issue.
Okay.
And yeah, these are some of the more analysis, which, yeah, I think it's not that important.
No, that's fine.
But yeah, I want to spend some time on these graphs. So here on the left side, we try to compare these two methods, where in one, we are using logistic regression, and in other, we are using metric learning to produce the final output. And as we can see, their performance for each of the class, when we are using metric learning, we are seeing kind of very huge improvement in small and large class. So this again showcases the fact that since we are kind of addressing that problem explicitly, we are seeing huge improvement in that area. Then in the second graph, we basically try to see performance on products with let's say, which had less than 2 transactions, or which had less than 5 transactions, or less than equal to 10 transactions, or which had many transactions. So we performed classification on only those data points, and we compare our method with the baseline method from Amazon paper. So here we can see, so essentially when we have less transactions, so that is essentially a kind of cold start scenario, that we don't have much information about the customers, so we might not be able to perform very well. So as we can see here, although the overall performance is 0.6, which is not very good for AUC, but in comparison with the baseline method, we are performing quite well, which could be attributed to the fact that we are learning more features and better features. And as we get like more data, we can see the baseline method improves uh, significantly. Yeah. So yeah. So as we chatted earlier, like one of the future directions is to try to build interpretability into the model. So one avenue to do that is to kind of utilize the review text we have and somehow try to incorporate it with our latent features, so that we can know of what those latent features mean, and to also capture where to put more focus on. So to motivate that, I think this graph is very good. So this is essentially the metric space, and center is like fit transactions, small transactions, large transactions, and we kind of picked few transactions, and we tried to measure the cosine similarity between the representations, and we also tried to look at the review text. So if we take example of these two transactions, so the similarity is 0.99, and if we see the review text, it says that it's tight in the shoulders and too big on the waist, and this says that it didn't accentuate my waist, as in it's like big on the waist. So essentially we are seeing similar kind of feedback for the transactions which are kind of closer in the metric space, and if we compare these two which are kind of farther apart, we can see that there is not much overlap. And similarly, there are a couple of other examples. So one of the challenges here would be that not all the transactions would have review text, and not all the review text would be much descriptive of the fit feedback. They might be talking about the quality of the clothes that was used for the product or something else. So that is like one of the challenges in applying language model to try to make sense out of these latent features.
Would you apply the language model as a separate training system? So once you've actually got your metric space, you would then try and
no. So
okay.
no. So there's I've referred to one of the papers. So here explicitly authors try to have a kind of a single objective where they have latent factor model, and they have a language model, and they have some constraints which tie one latent variable with one of the topics in the language model. So they have like a single objective which they try to learn from the feedback data and the review data.
Very
So
cool.
yeah, this is a very interesting paper.
Mm.
But yeah, again, the challenge here would be that in review text, the fit feedback might not be very descriptive.
Have you done any work with computer vision in terms of analyzing visible features of either the customer or the products, or you're just using?
No, because yeah, we didn't have that kind of data,
Okay.
which is the problem.
No, yeah, I mean, that's the space I work in, so it's very powerful. But, very
Yeah.
interesting. So I did have a question from reading the paper. There's this implicit assumption that you can use Euclidean distance as a way of comparing the similarity of things. Is that, I've never seen that before. Is that something that is well understood, or is that an assumption that you made, that the Euclidean space is good enough for the purposes of the metric learning, or just
So
curious?
yeah, I think you might have misread because we said in the paper that Euclidean distance is not a very
No, I
good
agree. Yeah, I agree. Yeah.
measure to select the target neighbors. So that's why we have this prototyping technique, so that we can alleviate this problem somehow, that we are applying some heuristic and we have only good target neighbors available. So even though there is some limitation with respect to Euclidean distance, we'll only be selecting like good neighbors. So if we apply metric learning here versus here, like here we'll have like more chances of getting good neighbors.
Excellent. Well, thank you very much. Were there any other questions? I don't know who else has joined. I don't quite know if anyone else is out there. We've run out of time, so wow, that's very interesting. So, so are you continuing to work on this? Are you going to be publishing new material in this area?
So I'm working like full time and I'm focusing on some other projects.
Oh,
But
okay.
yeah, if someone can, collaborate with me, so probably I'll be able to spend some time.
That's great.
Because yeah, by myself now it's harder than it was in graduate school.
Yes, I understand.
Yeah.
Yeah, very much so. Well, that's great. Well, thank you very much. And we will basically, if you have any questions, we'll be posting this in the Slack channel as a video, and we look forward to hearing back from you. So thank you again for presenting. And
Yeah, thanks a lot. So I'm also in that Slack channel. So if someone has any questions, they can post it there, and yeah, I'll be happy to answer.
excellent. All right. Well, thank you again. All right, everyone.
Yeah.
Bye for now.
Thank you.
Okay. Oh, sorry, there was someone there. No? Okay. Anyway, all right. Thanks, Ryan.
Yeah, I just wanted to thank David and Rishabh for your efforts. Thanks. Bye.
Yeah, thank you.
No problem. Okay. All right, everyone. Bye.
Yeah, bye.